Packet processing is what makes the internet work. If we look inside, we see cables. They might be copper cables or optical cables with bits, binary digits flying along at very high speeds. But what these bits form are so-called packets. These are the things like envelopes which carry your data from one place to another on the internet. And as the internet's evolving, what we're seeing is far greater needs for packet processing. It used to be just simple switching and routing to get the packets from A to B via some intermediate points. That means being adaptive and differentiated, so the packet processing changes depending on network conditions and the kind of traffic that's passing over the network and the contents of the packets, what type of traffic it is. Is it video, is it email, or is it something else? So packet processing is becoming a lot more challenging in terms of the functions. We need more smartness, more programmability. But also the data rates of the wires are getting higher and higher. Currently we're looking at 100 gigabits per second. That's 100 billion bits per second. And we're heading towards 1 terabit per second. That's 1 trillion bits per second going over the wire. And it's very challenging to actually process packets at these kind of rates. This is where the Xilinx FPGA can play a role. It's a technology that can go at hardware speeds, but has the programmability and flexibility to implement the modern packet processing functions that are needed. Let's have a look at some of the basic things we do with packets when we're processing them. The first one is so-called packet parsing, and that's having a look at the bits going over the wire and just figuring out exactly where the packets are, what's in the packets, where they're going from, where they're going to, and generally trying to analyze the contents of the packets so we can decide what to do with them. And that's very challenging because packets have different formats, different positions in the bit stream, and we have to do this at these very high sort of gigabit towards terabit rates. Once we've done packet parsing, we've usually got some interesting information from the packet, and then we do packet classification. That's deciding exactly what kind of packet it is and what we're going to do with it at the next step. Packet classification usually involves lookup tables, content addressable memories, taking some information from the packet and getting back some instructions on how we should process it, how we should send it on to the next point in the network. Before we do that, we often do packet editing. That's where the packet actually gets changed. We might change some of the contents of the packet. We might even insert new things so the packet becomes longer. We might remove things so the packet becomes shorter. It's the kind of thing we don't normally do in the regular letter post. Once you put something in the mail, it's going to come out the way it went in. But in high-speed networking, we often change the packets en route depending on where they're going and what their purpose is. And finally, there's packet management or traffic management, which is where we schedule packets to decide who gets to go first. We only have limited capability to send packets to other places. Some might get more priority, for example, if it's real-time video, versus something like email, which isn't so time critical. So we have to schedule and also sometimes police and shape, which is making sure things don't misbehave by sending too many packets in one direction at the same time. So taken together, these are all functions which the FPGA is very good at. It can operate at the wire speed because it's hardware, but it's very programmable, so we can get a lot of flexibility into these functions. And we do that via programming interface. Either we have some kind of API which allows software to change the packet processing, reprogram it, maybe reconfigure the FPGA completely and change the hardware. And we can have high-level languages for expressing the packet processing so that users don't have to know about the hardware details, but can just write down rules they want to apply to packets, and that gets translated into fast hardware implementations. So this is going to get more and more important with modern networking increasing smartness. For things like security, where we have to check out for rogue packets, or things where we're doing content addressable networking, where we want to look at the contents of the packet and decide more deeply what to do with it, rather than just forwarding it without changing it. All of this is going to make more and more demands on packet processing as we go forward in the future. And the only real way to tackle this is using high-speed programmable hardware. So in summary, what the Xilinx FPGA is providing here is what you might call the 3 S's: speed, smartness, and security. All of these 3 things are very important for modern networking, and all 3 are posing increasing challenges which the FPGA is well positioned to address.